Hi everyone, my name is Yannik and I will today talk about efficient exact inference with noisy data using the primary estimation method ABC. Or a bit more pointed, how to noise up your ABC. If you want to follow the talk more interactively, you find the slides and further info prior to the talk, also at the sites indicated at the top. Let me start with a short graphical abstract. I will consider the quite common problem that data are not perfect but noisy, and illustrate what problems this can cause in ABC inference. To deal with noise, there exist different solutions, of which I will focus on the third one, here called stochastic acceptor. It has some really nice properties. The main contribution will then be to turn this concept into an efficient algorithm using tempering. At its core, on the left, the main takeaway might be that noise in ABC is maybe against intuition, not a bad thing, but it actually allows to perform exact inference. To set the stage, what is actually ABC? Approximate Bayesian computation. In my group, we often consider mechanistic models of biochemical processes, using, for example, Markov jump processes, SDEs, or agent-based models. These models typically depend on unknown parameters which we need to infer from available data. However, for complex stochastic models, we often cannot even compute the likelihood of data-given parameters. ABC is a simulation-based method to reliably perform inference in such kind of desperate cases. All it requires is some sort of black box where you put in parameters and get out simulated data. In ABC, we now sample parameters from the prior, put it into the model, and accept if the simulated data are sufficiently close to the observed data, according to some distance function and some epsilon threshold. If not, we reject. Doing this a couple of times, it can be shown that we obtain a population of accepted particles which are sampled from an approximation of the Bayesian posterior density. Put into formulas, we want to infer the posterior, but we don't have the likelihood marked in red here. What we get in ABC is the below distribution, using an approximate likelihood. I feel compelled to here add a little disclaimer. Operating on a black box, ABC is a very broadly applicable method and used in different scientific areas. But it is in particular often computationally quite demanding. It may not be the best choice for all models in all situations. So let's talk about noise in ABC. It is rather common in systems biology that data are not perfect but noise corrupted. However, we have seen that in practice, and ABC kind of invites to do so, noise is not considered in the analysis, with statements like, to avoid assumptions of a normal likelihood, we use ABC, or ABC does not use a likelihood. However, this is not really true and can cause problems, as I would like to shortly illustrate. We assume that the forward model we simulate from does not account for noise, but that the data are noisy. Here in the bottom row in green and purple, I guess you see two results of standard ABC analysis when this noise was ignored, while letting the epsilon threshold go to 0. Basically, the result is point estimates at the maximum likelihood values corresponding to whether here we used L2 or L1 distances. This is definitely far from what we would hope for in a Bayesian analysis. Only if we correctly account for noise, here shown in orange, we obtain the correct posterior distribution, which also makes sense. Okay, this was here illustrated on a very simple ODE model, where the effects are maybe overly simplistic. However, also for other types of models, we did observe that often we obtain seemingly confident, but especially if we know the ground truth, just wrong parameter estimates. Basically assuming that we have perfect measurements, which is in practice hardly the case, right? So how can we account for noise? To account for noise, different approaches have been employed in the past. Either, first, the epsilon threshold can be chosen such that, for example, its variance matches the real noise variance. This, however, effectively translates to assuming uniform noise, which is not that common a noise model in practice, right? An alternative is to take the model output and add random noise to it, as by approach 2 here. And then you can also let the epsilon threshold go to 0. The third alternative is to modify the acceptance step away from this binary distance epsilon thingy towards a criterion based on the conditional probability of noisy data D given noise-free model output Y and parameters theta. This is based on a famous paper by Richard Wilkinson, who stated that ABC actually gives exact inference just for the wrong model. Namely, a model with model error induced by the acceptance step. Why do we want to use this approach? Well, it has some nice theoretical properties. Namely, it can be shown that if you base the acceptance step on the true noise distribution, you can actually perform non-approximate exact Monte Carlo inference. So you can strike through the A in ABC. Intriguingly, this is made possible by the non-trivial noise distribution, and although we still don't have the complete likelihood. Here we have generalized the statement by Wilkinson to arbitrary noise distributions, and in particular allow the noise model to be parameter dependent, which will be of interest later on as well. So we implement this method. However, we encountered practical problems. Namely, it just doesn't scale well. For a very simple two-dimensional ODE model, here we did an evaluation/prediction of how many simulations we would need for different numbers of data points. And quite frankly, 10 to the power of 200 something simulations is not really feasible. The method also didn't work for more complex models. Thus, we looked at what can be improved. And spoiler alert, this is what we obtain for the method we then developed. We see here orders of magnitude less simulations, which really makes this usable in practice. So how did we do it? In the following, I would like to describe a few main algorithmic aspects of the method we ad hoc labeled ASSA, Adaptive Sequential Stochastic Acceptor. ABC is frequently integrated into a sequential Monte Carlo SMC scheme, where one iteratively reduces epsilon while sampling from an increasingly better approximation of the posterior, moving from generation to generation. This allows to reduce the epsilon approximation error while maintaining high acceptance rate. This has been shown to be often far superior to plain reduction ABC. So in our exact formulation, what can take the role of this epsilon decrease? We don't have an epsilon anymore, after all. What we did here was to temper the acceptance probability in each step, starting with a high temperature, which indicates to 1 eventually. You may see certain similarities to MC-MC parallel tempering. However, there are still two main problems. First, in order to have an acceptance probability value between 0 and 1, we need to divide the probability pi of d given y and theta by some normalization constant c, which we need to know. In the past, it has been suggested to take for c the noise probability at y equal d. However, it is often not really likely for the noise-free simulations to exactly reproduce the noisy measurements. Meaning this C value is far too high, leading to low acceptance rates. An alternative is to choose the empirical highest peak. Practice is, however, usually not known. In our sequential approach, however, we can adaptively, iteratively find good and better values for this peak in a self-tuned manner by, for example, just taking the highest value found so far in previous generations. If the value we pick is, however, not large enough, such that we end up with values greater than 1, this introduces a bias, as former papers have also pointed out. However, we can correct for this bias by reweighting our accepted particles, as shown here by the term in red, using ideas from rejection control and burden sampling. Also practically, in the plot here, you see that when we don't account for the bias, we don't correct for it, different normalization constant C values reside on different flattenings of the posterior. However, using the reweighting as by the blue line, we exactly reproduce the true posterior, even for low C values. A second problem is how to choose the temperatures T. This would kind of balance information gain and cost per step. A particular scheme we develop is trying to fit the temperature T such that a predicted acceptance rate based on previous simulations matches the target value. In particular, this scheme then also allows to choose the initial temperature, which is a crucial tuning parameter usually. As you see here, on the left-hand side of this plot, this rate prediction here trying to match a value of 0.3 seems to work based on the information we have. And on the right, you see the importance of, in particular, the initial temperature. Choosing it too low leads to a high cost in the initial step, while a too high value leads to gaining no information in the first few iterations and just wasting computation time. Our method, in turn, reliably finds good values here. Here you see how the temperatures we propose lead to a smooth transition from the prior to the posterior. So we seem to have a okay information gain per generation. Let me continue with showing some results. We applied the algorithm to various model types, including ODEs, SDEs, Markov jump processes, and age-based models, and noise models including normal, Laplace, and Poisson noise. Then we benchmarked the algorithm against various alternatives. So here in blue, we have the proposed ASA algorithm. In orange, the approach where we add noise to the model output, so approach A2 from beforehand. In green, we choose the normalization constant C too high, basically to Y equal D. In red, we use a non-sequential approach, so just one generation. And in purple, a non-sequential approach with this too high C value. This is basically an extension of Wilkinson's original approach. You see that for all test models, our approach seems to perform best. And don't forget to label your axis. Here we show a log scale. So our approach actually needs at least 2 times less, sometimes between 10 and 100 times less, and for M2 and model M3, up to an extreme 10 to the power of 20 times less simulations. As you saw before already, this approach also scales well with the number of data points. So here it is really a step from theoretically interesting, but cool, I guess, to actually practically applicable. We also applied the method to more challenging problems. Here to an ODE model with 11 parameters, including 3 noise parameters, which we can infer on the fly alongside the other parameters. And not shown also to an age-based Cantor growth model with 7 parameters. Here we could only compare ASA to the noisy model approach, where we add noise to the model output. And consistently, ASA performs superior, even though the other approach was given more simulations. Last point, we also implemented ASA in the ABC SMC open source toolbox by ABC, which we developed in the group to also make it usable for other researchers. To summarize, It is intriguingly the non-trivial noise model that enables exact likelihood-free inference in an ABC framework. Here we developed a widely applicable sequential algorithm, which showed orders of magnitude speed up compared to alternatives. And in addition, the algorithmic details make this also quite nicely self-tuned, so having to set no hyperparameters at all. I'm happy to answer questions and discuss details, either after the talk or separately. Thank you for your attention.